What's it for?
Is the screen visible?
Yes.
Okay. Hello, so today I'll be presenting the paper gDNA towards generative detailed neural avatars. Here are the contributions of the paper. So this was the first method to generate a large variety of animatable 3D human shapes in detailed garments that learn from raw post-3D scans without requiring canonical shapes, detailed surface registration, or manually defined skinning weights. And this was also the first to present a technique to significantly improve the geometric detail in clothing deformation based on recovering the underlying statistics of cloth deformation. So let's look into the core architecture. So yeah, initially we start off with defining the surface. So let's say in a 3D coordinate space, we will define the surface of a, so in this paper, they model human avatars. They predict their occupancy, sort of an occupancy field and also a normals field. It's sort of, the overall architecture would sort of look like this. It takes in some latent codes that I will describe later, and then some shape and normal maps are generated in 3D canonical space, which are then deformed to particular body poses and sizes to get the final normal map. So surfaces, we will define the surfaces as 3D points for which an occupancy network has a value of 0.5, where this occupancy network is just gives the occupancy probability for any 3D point X in canonical space. So this occupancy network takes as an input a 3D coordinate point and the latent shape code Z, which has to be sampled. And then it predicts this 3D feature map from which we do trilinear sampling, and then we use the sampled feature from the 3D feature map generated along with the 3D coordinate and feed it to the next segment of the occupancy network. So the occupancy network is just generally some 3D convolution operations, followed by some simple MLP. The overall, so this is how the occupancy network would look like. First, we take a latent shape code and get these 3D feature maps. And we get the we sample the segment of the feature map that is most closely associated to this query point, and we feed it to the MLP, which returns a value from 0 to 1. For surfaces, this is expected to be 0.5. And besides this value, it also returns some feature vector, which is fed to the next segment, and we'll get to that. So the Z shape latent vector is expected to represent the overall shape of the human, sort of the core shape. And then we have another latent shape called this Z detail. Z detail is meant to, so in this work, they model human avatars, which are clothed like as a normal human would be. So because clothing generally have some random patterns like folds, and they also tend to vary in appearance. So this Z detail is meant to capture those remaining details. So this latter part of the latter part that comes after the occupancy network, the normals predictor, takes as an input this feature vector generated by the coarse occupancy network and of course the coordinate point and the Z detail to return some normal vector n. So normal vector, I suppose, for those who are not familiar, in a 3D shape, you could think of it as mm, uh, in a 3D structure at a particular point, it would be the normal to the tangent at that particular point. So as long as we have any kind of 3D representation, if we sample 2 points that are close together, we can technically uh, manually compute the normals from those points by calculating the gradient along that point. But that would be computationally expensive of source, so they just do it using an MLP here. And then we will get to single subject forward scanning. This refers to, let's say, first using the using the network I just described, this canonical implicit model, we have shape representations and normals representation in a canonical space. And this for every single, for any person, for any basically this Z detail and Z shape that has been sampled, this canonical representation pose is going to remain roughly the same. And this is a hyperparameter. We can choose which pose to represent this in the canonical space. And then the next part comes in where we take this representation in canonical space and then we apply deformation to match, to sort of map it to the pose that we desire. And this deformation is described as this is done by simply blend skinning operation, which is common in this field of work. Blend skinning simply refers to, let's say, we have, just to give an example, in a 3D structure, we have some joints or some vertices or some points that we can define. And usually in case of humans, those joints would be the bone joints in the skeleton. And so this simply refers to, let's say, we have representation in this canonical pose. And then when we apply a particular deformation, the linear blend scanning means to find out to what extent the 3D structure or 3D points around a particular joint is going to be deformed or bent to create the pose that we want. So, but this is for some points in the body. There are multiple joints close to it, and multiple joints can influence to what extent that part of the 3D structure is going to be deformed. Hence, this linear blend scanning operation, it simply takes sort of a linear combination at a particular point of influences of different bone points to find out to what extent, or what's the resultant effect of all the joints in the body. So when in previous work, the standard procedure used to be to, so let's say here this W would be the skinning field network of sorts, the deformation network. So usually what they would do is take a point in the canonical space, a 3D coordinate, and then map it to some weights. And this weight would be, of course, using softmax, this would be restricted to between zeros and ones. the individual values of the components in this weight vector. And of course, they would sum to 1 as well. And the dimension of the vector would be equal to the number of bones. And then the reason they do this in canonical space is because, and not in the global space, is because defining skinning field, skinning weights field in canonical space is, if you do this, then this deformation, this representation becomes sort of pose independent and easier to learn, and it's easier to generalize to out of distribution poses. But in this paper, they do multi-subject forward skinning. What this means is that the network, their approach learns to do this deformation on the canonical space by aggregating the information over multiple subjects. So what happens is, let's say if we have many people, but we don't have nearly as many scans of each of those subjects, since we have a commonly defined canonical space that this network learns to deform, even if we don't have multiple scans, but as long as we have a lot of people with fewer scans, we can still do this pretty accurately without needing a lot of scans for a single person. So that's what multi-subject forward scanning refers to in this case. The effects originating from the body size variation beta and the clothed human shape Z shape is decoupled in this module. So basically what this refers to is that let's go to the overall architecture. In the overall architecture, to deform this 3D shape to desired poses, they take in two parameters, the body pose theta and the size parameter beta. So beta is a 10-dimensional vector that would represent, I suppose, the size of different parts of the body, and theta is simply associates to the angles between different joints of the body. So this multi-subject forward scanning module they claim is independent of the body size, and we'll see how they do that. So to capture diverse clothed human shapes, the skinning field on the latent shape Z code is expressed like this. We have this network which takes as an input 3D coordinate and the Z shape and returns the blend skinning weights. And then given a point, and then they have a separate space, this is more of a space which is a resized version of the canonical space. So this, so let's see one thing, because as you can see, this canonical space is generated before this body pose and theta is given in. So in this canonical space, body size is roughly an average of all the sizes of all the subjects. So after we have these parameters, we have a separate body shape space where the size would be, I suppose, more closely associated to the size parameter that we have put into this network. And then given a point x hat in B size space, the warping field maps it back to the mean size by predicting its canonical correspondence x. So this warping field network, its job is to take a coordinate in this beta size space, in this resized beta size space, and then find the corresponding 3D point in the canonical space. And yeah, as an input, it takes of course, the 3D coordinate and the body size parameter. And both the skinning field and the warping field are just MLPs. And the final resized canonical surface is now hence defined like this. This S hat would be the set of 3D points which define the surface in this new beta size space, where the given the Z shape and then this 3D points in the beta size space mapped back to the canonical space would return an occupancy value of 0.5. And then given the target body pose theta and a point x hat in beta size space, this is transformed to post space x hat via this operation. So the post space x hat is simply the coordinate in the deformed space. So given a 3D point in the beta size space, we find this D function, this deformation operation refers to where that point would go after it has been deformed. So this deformation operation is can be expressed like this. This linear combination of scaling operation on which is a weighted average of sorts of all the bones. And this bone transformation matrix here is, you can think of it as something that we can derive for every single bone using the beta parameter and the theta parameter. So this is pretty much this illustrates pretty much all the operations in this multi-subject for skinning module. So this module deforms the canonical occupancy and normal field to the target post theta and size beta by establishing correspondence from post space x hat to canonical space x star. First, given a deformed point x prime, we find its corresponding in resized canonical space x hat star by iteratively finding the root of equation 9, which we'll see later. Subsequently, we map x hat star to x star in size neutral canonical space using the warping field. So I'll get to all the issues discussed here in detail. Given a point x hat in this post space, we need to determine its corresponding in canonical space x prime to compare the predicted occupancy and normals to ground truth. So what this refers to is, so in this beta size space, let's say we take a 3D coordinate, we will first find the deformed point after it has been deformed, and then, but since the occupancy network and the normals network are defined on the canonical space, we have to find for a point in this deformed space, x prime, we have to find which points in the original canonical space corresponds to this new point in deformed space. So for one point, for a particular 3D point in this deformed space, there can be multiple corresponding points in the canonical space. The way this happens is because when we deform a 3D structure in canonical space, since multiple points of the body can come in contact with itself, when we deform them, there are multiple points in canonical space that are deformed to meet at a particular point. So, which is why we can have multiple points of correspondence for a single point in the deformed space. So then now the job would be to find those points of correspondence in the canonical space, because as I mentioned, the normals and the occupancy networks are defined in the canonical space, not in the deformed space. And then following the previous work, SNARF, this problem can be formulated like this, where D is the deformation operation and x prime is simply the point in this deformed space. And this problem does not have a closed form solution. So we need to follow an iterative approach to find all the points of correspondence. You can find, if you're interested, you can find more about this formulation in the SNARF paper. So in the end, the points of correspondence can be represented like this, where we find first the points of correspondence in the beta size space, and then we use the warping field to map it back to the canonical space. So far, we have come up to about here. We took some structures in 3D canonical space, and we define this beta size space, and then given the body pose and the body size parameters, we can deform them, and then we find the points corresponding to the deformed points in the canonical space, and then we get the occupancy and net normals output. So now this value of this normal vectors in the deformed space can be found with this operation, where this Ri denotes the rotational component of the bone transformation matrix. And yeah, overall, following the notations, all of this operation can be expressed in this way. And then comes the next module, the implicit surface rendering. And because this work maps clothed humans, geometric clothing details which are challenging to learn due to their sort of random nature. And since in 2D image generation tasks, GANs have achieved impressive results on learning high fidelity local texture, they propose using adversarial loss to supervise the normal maps that are generated. So even though this whole everything up to the rendering point is mapped in 3D space, the supervision is actually done in just 2D space. So to generate a normal map from a particular viewing point, given a pixel P in the 2D pose normal map, its correspondence in deformed 3D space X prime can be determined by intersection between the ray through P and the forward skin surface. So so basically, we pass a ray through a pixel P into the 3D space, and we find the objective is to find the point along that ray where it hits the surface of the 3D structure. So that would be the point of intersection of these two formulations. And in this ray formulation, of course, the RC refers to the origin of the ray, and RD refers to the direction of the ray, and T is simply the parameter to move along the ray. And once the X prime is the point of intersection is determined, well, this X prime can be determined using the secant method, the point of intersection between the ray and the 3D structure surface. And then, yeah, the 3D normal that's map that is generated in this manner for every single pixel in this image we're trying to form, we can just represent it like this. And here are the losses involved in this network, where this bone loss is just the binary cross entropy loss between the output of the occupancy network and one. These two networks are only applied during the initial phase of the training, where this is defined over where the W joint and W target, this X bone are randomly sampled on points on canonical bones. So this would only be points where, when we train using this loss, those would only be points where we know for sure that the query points are on the surface. So, which is why we can say the ground truth in this case would be 1, and we apply the binary cross entropy loss. And for the joints, or to supervise the weights, blend scanning weights that are generated, what we sample points sort of at the we set so that for a particular point on the skeleton, the two joints that are closest to that point, so basically the joints of the particular bone that the point is in, for those two joints, the skinning weights are set to 0.5, and for everything else, it's set to 0. Basically, they assume that for a particular point on the body, only the two closest joints have influence when it comes to deforming that particular 3D point. The other bones don't have much of an influence. And then this L warp is, and then for the next loss, we get this by first getting this ground truth V of beta naught, which is found by, since these both the beta parameter and theta conform to the SMPL formulation of a human body representation, these are formed by, this can be, basically this ground truth can be found from the mesh. And then comes the next loss, the L norm for the normal map that we generate. This is simply the dot product of the ground truth normal and the predicted normal. And if they were exactly the same, if the directions were exactly the same, the dot product would have been 1. So we just find the gap between 1 and our dot product of our prediction. So, and then going to the experiments, they use the Sizer dataset to evaluate the fitting. The dataset contains 3D scans of human in 21 garments, including shirts, t-shirts, coats, and pants. So on the top frame, it's the representation that they generate in canonical space after Z detail and Z norm has been sampled. In practice, those values, the Z norm, the Z detail and the Z shape, can be calculated for a particular person using some prior work that have done this. And when training, both that network and the proposed pipeline are jointly trained. So for a person, they can determine what the Z shape and Z size would be for a particular person. So once they have generated their representation in the canonical space, we feed the host parameter and the size parameter and deform these persons. And yeah, these are the results after deforming the generated 3D structures above. And they also present results for interpolation. What they argue is that once Z detail and Z shape has been sampled for a particular person, once they change them, the change in the appearance is rather smooth. And for disentangled generation, here they keep, I believe, the coarse Z shape, they keep the Z shape constant along everything, and they just change the Z detail. And as they show, the coarse shape or the size of the person or the shape of the person remains unchanged, and only the finer details like these wrinkles on the clothes and such kind of details are changed only. So the Z shape and the Z detail are very well decoupled in this proposed framework. So that's it for me. Thank you all for listening.